We will talk about OCaml and probably the next version to come. Welcome.
Okay, so thank you, Sylvain. Can you all hear me? Okay, so we are welcome to this meeting, and thanks for coming. So yeah, I'm going to tell you what's been going on and what is going on right now in the around the core CAML system, and what we've been doing since the last meeting, what we are going to do in the coming weeks. Before that, let me thank a few persons who were instrumental in getting this meeting to happen. First and foremost, so Sylvain Legal from OCaml Core, who for the third time did most of the organization. Then there's Inaya, Paris-Concours Conference Bureau, and especially Mrs. Chantal Giraudon, which is sitting just outside, for the local arrangements. And this is all funded by the CAML Consortium. So you see there are some uses to the CAML Consortium, like paying for this room and a nice lunch you're going to have at noon. All right, so so this is what I will be talking about. So rather briefly, a few news about the development of CAML, our various releases. Then briefly again, some news about the CAML Consortium itself. And so most of my presentation will be on describing the new language features that are to appear in OCaml 3.12, and there are surprisingly many. And then some remarks to conclude. All right, so let's start. So recent releases since the last meeting. So two minor releases, bug fix releases, 3.11.1 in June 2009, fixing about 45 problem reports. And another one, 3.11.2 in January this year, fixing about 32, and with quite a few improvements on and updates on the debugger, OCaml debug. So thanks to Xavier for his work. And a few old feature wishes were granted. All right, so that's kind of routine. So the next release will be a major release, 3.12.0, with again surprisingly many new language features. Well, that's a teaser for the end of the talk. More bug fixing, more wish granting, and we've been careful to preserve backward compatibility. So currently there's only one known and voluntary backward incompatible change, and that has to do with the string to integer conversion functions, which used to accept the string literal representing max int plus 1 and silently turn it into min int. So there were bad reasons for doing that, and those have gone. So now that those functions will fail in this particular case. And I hope this is not going to break too much of your code, but well, we will see. All right, so here is the tentative planning. So I'm happy to announce that that we've done a feature freeze. So now we know what's going in. And so in the coming 2 months, say, we will finish merging. So some of those new features are still on branches, writing documentation, updating CAML P4 and OCaml doc accordingly, and doing more bug fixing. I hope to have a first beta release in early June, or maybe even late May, and for a final release in early July, before the summer break. And as usual, well, testing and feedback from you is much appreciated. So either if you track the Subversion trunk, or at least when we release beta versions. Okay, so a few words about Manpower. It's always been the Achilles heel of OCaml's development. So it is on the rise, especially thanks to external contributors. So Alain Frisch from Lexify did a lot of work on the new features, and more recently Mark Shinwell from Jane Street also joined the OCaml development team, and we are very happy to have both of them on board. And then there's the usual suspects, so the historic INRIA team, that makes me feel very old. So especially Damien Deliger and I. So Jacques Garrigue, who's at Nagoya University in Japan, is still active, and some of the new features were actually developed by him. And then, as I mentioned earlier, so we have Xavier contributing as well. So he is an INRIA research programmer, and he splits his time between several research projects, and one of them being CAML. So in the end, we have the equivalent of about 1 person full-time, which is still about twice as much as what we had 2 or 3 years ago. And I'm also glad to announce that the legal status of contributions from outside INRIA was clarified, and the answer is called a contributor license agreement. That's basically a piece of paper that says well, that you, the contributor, keep the copyright, but you grant INRIA the rights to do whatever it pleases with your code, and you also give up on any patent claims, if any. And so that's kind of a standard procedure. The Apache Foundation, for instance, uses this for all its contributions. For all its contributions, but it's still more lightweight than the copyright assignments that the Free Software Foundation use. In a copyright assignment, you give up all your rights on your code, and that doesn't fly well with French law. Okay, so so that's one less thing to worry about. All right, so a few words about the consortium. So we have one new member this year. It's ML State, which is a startup company based in Paris and doing web programming, let's say, server-side web programming. I don't know if anyone from ML State is here today. Okay. So you may know David Teller, for instance, from his work on batteries, and he joined ML State recently. And so that brings us to 11 members total. That's getting respectable. So this is a list of all members, and as you see, it's a fairly diverse bunch, ranging from a one-person company, OCaml Core, to many-person companies like Microsoft and Intel. And the kind of things they do with CAML is relatively varied as well. So, for instance, there's Dassault System basically implements a domain-specific language. Microsoft, CEA do static analysis tools and program verification tools in general. So Lexify, Jane Street, and SimCorp are all in the finance industry. So Jane Street is a trading firm. Lexify and SimCorp provide software for the financial industry. Citrix uses CAML to develop system administration tools for the Xen hypervisor. And, well, did I forget anyone? Yeah, and basically Dassault Aviation and Intel, well, don't really use CAML at this point, but well, wish to support it, and well, have a general interest in new programming languages for Intel, and in formal methods and verification tools for Dassault Aviation. Okay, and so just to remind me, the actions of the consortium. So what it does, first and foremost, is to sell a permissive license on the CAML code base. So it's basically a BSD license, and it lets members do pretty much whatever they want with the code base. So in this sense, it's much less restrictive than the default LGPL plus QPL license that CAML has. So it's a lightweight way for a corporation to sponsor CAML a little bit. it's intended as a place to discuss needs with power users from industry. It's good for public relation, or for us to justify our work with respect to INRIA, for potential industrial users of CAML, who may be reassured by seeing so many famous names as members of the consortium. And then it brings some pocket money for the general operation of my research group, which is most welcome, and also for paying for internships and sponsoring this meeting, for instance. And so what is relatively new this year is that actually, so this part, the discussion of needs and actions, is really working well. So nowadays, the consortium acts very much as a sounding board for discussing new features and needs. As I said, we have two members that contribute manpower and can contribute directly to the CAML code base. So we had a meeting, so we have a yearly meeting. The last one was in December 2009 in Paris, and it was really well attended. So 12 participants, 12 outside participants, plus 4 INRIA persons. So some of the participants came from New York and London and Copenhagen. And we had some very good discussions of possible extensions and future developments, majority of which materialized in 3.12.0, and those kind of discussions continue on the consortium mailing list. All right, so now the part that you've been all waiting for, it's the description of the new features. So that's a long list. There's no less than 8. So let me go through them relatively quickly, and then I'll leave time in the end for if you want to go back to some examples or things like this. All right. So let's start with a small bit of syntactic sugar about records. So in record patterns and record expressions, so you can write just ID instead of ID equals ID, and m.id instead of m.id equals ID. So here is an example. If you open the complex module, you get a type of complex numbers, which is a record with two fields, RE and IM. And well, here is a way to construct a record. You can just say RE IM, and that really means RE equals RE, IM equals IM, and so if RE and IM are regular variables that are bound earlier, those values are automatically taken to fill the fields. And likewise, in a pattern, if you write RE IM, that stands for RE equals RE, IM equals IM, and that is going to bind local variables RE and IM to the values of those two fields, and now you can use them in the right-hand side as before, or with the new syntactic sugar. So, well, that's no big deal, and it's been in standard ML for a very long time. But, well, it's still notationally convenient. So another bit of notation for records is that now at the end of a record pattern, you can put semicolon underscore. That annotation means this pattern doesn't list all fields of the record type, but this is intentional. And so, continuing the complex example, so if you write a pattern that only matches on the RE field but not on the IM field, then you will now get a warning if warning R is active. So don't worry, it's turned off by default. So, however, if you want to silence this warning, you can write explicitly semicolon underscore, and that means that tells the compiler that yes, it is intentional that not all fields are listed. So this will never warn. And so what's the usefulness of this? Well, the idea is that, well, if you have some record patterns that you intend to be exhaustive, to list all fields, and then later you extend the record type with some new fields, then the compiler will warn, and that can be useful to basically see if something needs to be done at that part in your code. And again, well, all this is turned off by default. So if you don't like it, just don't turn the warning on, and it will work just as before. Number two is kind of similar in spirit. So tell the compiler a little more about your intent so that it can produce better errors and warnings. So it's in the class and object language, and so we have a new construct, method bang and val bang and inherit bang, which, so method bang, it defines a method just like the regular method keyword does, but it tells the compiler that you intend to override a method of the same name that's already defined in a superclass. So here, for instance, we are subclassing from class C, and if we say method bang M, then you will get an error if C doesn't already define a method named M, okay, if no overriding takes place. And symmetrically, if you define a method N, which is intended to be new, and you will get, you can get a warning if actually C defines a method already, and that method is called N. And again, this is a warning that is turned off by default. So similar annotations exist in other O languages like C#, I believe, and it's quite effective at catching misspellings. Basically, you wanted to override a method, but you got the name wrong, or things like stupid things like this. Okay, so here you will get a little more help from the compiler. All right, so let's move on. Oh yeah, an old favorite. It's the local open. So the ability to open a structure and bring and lets you use its components with short names, but within the scope of an expression. Okay, so like here you're opening complex, and so you can use short names for RE and IM. So well, it's been asked for a very long time, and I caved into popular demand. And also, well, there is a CAML P4 extension that implements this using local modules, but it's not very robust. In particular, if your expression here contains type variables that cannot be generalized, then you get an error, I think, with the CAML P4 extension because of the struct that you have to put around. While here, well, it just works like a regular let. Okay. Question? Comment? Okay. And while we were at it, so Alain Frisch suggested some syntactic sugar for let open M in E, which is just M dot parenthesis E parenthesis. So, well, if you're familiar with Christophe Troskler's delimited overloading package, that will be familiar to you, but well, it's much less powerful than Christophe's package, but still it has a little bit of the same flavor. So the idea is that, for instance, if you have a module float that defines the usual arithmetic operators, plus, star, etc., then you can do float dot, and then an expression where star, plus, etc. will be resolved according to those definitions. Okay. So again, if you want more, like clever interpretation of literals and so on, you're better off using Christophe's delimited overloading extension. But just this little bit of syntax can already be useful, and I think, well, I'd be interested to see what library writers or people who do, I don't know, the core library from Jane Street or the or batteries and so on could do with this notation. All right, so now for something slightly bigger, polymorphic recursion. So the gist of the extension is just that variables bound by let or letrec can now receive an explicit polymorphic type. So those explicit polymorphic types are written, quote A, quote B, quote C, dot type expression in CAML. And that really means for all type variables alpha, beta, gamma, some type. And so, for instance, if you want to define the identity function, you can declare it with this polymorphic type, and in this case that would be okay. But if you get the definition wrong, like here, then you will get an error. The compiler will tell you that this has type beta or int, which is not as general as for all alpha, alpha or alpha. And you should contrast this with regular type constraints. So if you just put ID alpha or alpha, this really means there exists some alpha such that ID has this type. And so in this case, this definition is okay, and alpha becomes int. Okay, and you get a function of type int or int. All right, so unlike regular type constraints, those polymorphic type constraints are reliable. Okay, so we know that the final type of ID will be exactly this and not something less general. So now we can use those optional declarations to type check recursive definitions better. Namely, we can now have recursive definitions where the recursively bound functions can be used at several types within the recursion, several different types within the recursion, and that's the essence of polymorphic recursion. And well, here is an example. Say you have a type of terms that contains in particular various association lists. So here is a list of string type time term, and here is a list of int time term, and then you want to recurse over those terms, do some processing, and with an auxiliary function, mutually recursive function, that is going to process lists, association lists. Okay, but here it will be called with a string type parameter, and here with an int type parameter. So if you try to write this in CAML today and you just erase this constraint, it's not going to work because you are using shift list with two different types within the same definition, and that's not allowed. However, if you put a explicit polymorphic type constraint, then the compiler is going to use it and see that everything is okay, those two calls are okay, and this definition is actually polymorphic enough. Alright, so that's a simple example of use of polymorphic recursion. So there are more advanced examples that involve so-called non-regular recursive data types. Basically type T, alpha T that recurses, for instance, on alpha list T. Okay, so T but with a different type parameter. So this you can write in CAML or in standard ML today, but you basically cannot write any interesting recursive function on it because it needs to be polymorphically recursive. And so now you can write functions over those weird and regular recursive data types, and they even have some uses. So if you look at Kazaki's amortized data structures, some of them actually use non-regular recursive data types. All right. Another really big one is first-class modules. So that's basically the ability to encapsulate a module as a core language value. Okay, so which then can be carried around just like any core language value, just like an integer or a function or a record. Put into data structures, put into references, whatever, and later you can recover the module from this value and use it in a module context, like as an argument to a functor or whatever. And so syntactically, so at the level of expressions, there is a module injection that takes any module X and an explicit type for it and returns a first-class value, whose type is this new form of type, module, some package type. And then in a context expecting a module, you can write val of an expression, which must have a module type, so which must be one of those first-class modules, and extract it with an explicit type. And so the types in question here, so these are not arbitrary module types because that would make type checking and type inference for the core language way too complicated. So it's a subset of module types consisting of a name, which is basically the name of a signature, something you've defined with module type s equal. plus optional constraints, so substituting some type components with some type expressions. And so, so this is basically an extension of an earlier proposal by Claudio Russo, which has been part of OCaml for a while. And so the main extension is that in Claudio's proposal, the package type was just a name of a signature. And so Alain added the possibility to change some of the parameters, to add some types basically as parameters. That brings useful additional flexibility. And of course, so those types are compared by name on this part and by structure on the toes. All right, so what can you do with that? Well, perhaps the most typical use is to select at runtime among several implementations of a signature. So here is a synthetic example. So say you have a program that outputs graphics in various formats. So you can define a type of module type of device, which is an output device with various functions. And then initialize a hash table mapping names of devices to first-class modules implementing this signature. Okay. And then, you can register various implementations of the device, like maybe implementation that generates SVG. And so you add to the table with the name SVG the first class module obtained from module SVG viewed with type device. And likewise, maybe in another file you will have a PDF output module that you will register with name PDF. And then, again, in some other part of your program, you can now parse the command line to see what device the user wants. Look up that name into the hash table. So that gives you a value of type, first class value of type module device, which you can then project into the module language using this val device constraint. And then you get a regular module, which you can bind and use later throughout your program. Okay. So that makes the module language a lot less static. Okay, you can really do more computations and more runtime choices when it comes to modules. So there are plenty of other uses, and if you're interested, you should talk to Alain Frisch, and he has some nifty demos to show you. So one example is to write functors that take a list of structures as argument of arbitrary length. So this has some uses in static analysis in particular, when you construct domains. And so that now will be expressed as a function, a recursive function that will take a list of first-class structures, okay, and produce a first-class structure. And but that can be written. You can do the recursive construction and everything. It provides an encoding of existentials, so first-class values with existential types. So it is an encoding, so it's slightly heavy, but the expressive power is here. And actually, more generally than just existentials, some forms of generalized algebraic data types can also be encoded. Again, at some cost in verbosity, but the expressive power is here, and the resulting code is reasonably efficient. All right, so 3 more to go. Number 6 is the ability to name types or type variables as parameters to functions. So basically, in the parameter list of a function, well, you can have variables, you can have patterns, but now you can also have this parenthesis type T parenthesis construct, which basically is a formal parameter, and the effect is that within the function the name T exists, and it's a new abstract type name. Okay, like, I don't know, like int or float. But outside, when you leave the scope of this declaration, this T becomes a regular type variable alpha from the core language, and then it can be generalized or instantiated as usual, following the rules of the core language. And so this parameter has no runtime effect, so no type is actually passed at runtime. Okay, it's just but it's a way to bridge module level constructs and core level polymorphism. And here is a simple example. Say you want to sort and remove duplicates in a list. Okay. So if that's a monomorphic list, if it's a list of integers, for instance, you could easily use the set module to do this. So you would construct using set.make a set of integers type, a module, and then you can insert all elements of the list in the set, and since it's a set, duplicates will be removed, and then ask for the elements of the sets, which is a sorted list. And so mission accomplished. The problem is that now, how to do that if you want this function to be polymorphic and work over any lists and given any comparison function? Well, now you can do this. So you're going to declare sort unique with one of those type S formal parameters, and then a comparison function over S's, and then a list of S's. And now S is a type name, okay, so you can use it to define a structure of, well, a structure that you can pass to set.make. So apply set.make to a type which is S and a comparison function which is a provided one. Then you can do the little hack I mentioned earlier, so insert all elements of L in starting from the empty set, asking for the elements. And at this point you get an S list as a result. And now, when you leave the scope, so S becomes alpha, and since it is generalizable, it is generalized, and so you get the expected type for sort unique. Okay, it's a regular type for a sorting function. Another example, declaring local exceptions in polymorphic functions. So exception E of alpha of quote A doesn't work in CAML, and for good reasons, because well, that would introduce unsoundness. However, you can do something similar but sound using this new notation. So again, so this is a function that basically just takes T and then a dummy parameter, declares an exception E taking T's within a local module, and then returns the injection function from T to EXN and a projection function from EXN to option T. And again, when you leave the scope of this T, it becomes a type variable, and it is generalized, so you get this type for new EXN. And then that kind of things can be useful, basically, to have an extensible data type for putting various data in it. All right, and that extension goes very well with the first-class module extension also. Okay, so the last two are also about modules, but more about the module type language and the language of signatures. So number 7 is the ability to recover the type inferred for a module expression. So it's written module type of M, and if you don't understand what that means, well, I guess you understand what that means, but it's basically M is any module expression, and module type of M is going to give you its module type, and it can be used in any module type context, in particular include in signatures. So the main use is to enrich the signature of an existing module. So say you take the hash table module from the standard library and you want to add some functionality, like this add all, that takes all bindings of T1 and insert them into table T2. then that can be written quite concisely. The implementation can already be written quite concisely. So basically you include the module hash table, and then you add the value fields you want. However, so until now, the writing an explicit signature for this myhash module was a complete pain, because basically you had to cut and paste the actual signature of hash table, okay, and add the declaration you want at the end. Oh, sorry, there's a bit of a typo here. So forget everything from the L to the first semicolon. Okay, and so now, well, you can write the signature for my hash just by saying include the module type of hash table. So that brings all the fields and types of hash table in the signature, and then just declare the new fields. Okay, and so we hope that will make it easier to basically enrich signatures a posteriori. And extension number 8, last but not least, has similar motivations. So again, it's how to do more things with signatures, and especially modify them or reuse them a posteriori. And so it's a new form of the with type, or actually with module also modifier that you're familiar with. So this new form is like this, so S, where S is some signature expression, with type T colon equal tau, so tau being a type expression. And the effect of this is to delete the declaration of the type T member from signature S, and then replace all uses of T in S with tau. Okay, so that keeps the signature well formed. And so contrast this with the regular with type constraint. So with type T equals tau, which you have today, and whose effect is to enrich the declaration. So it's going to change type T into type T equals tau. So the rest of the signature now knows that T and tau are more or less the same thing, but it keeps the declaration of T. So in this signature, you still have a T component, and in that signature, you don't have any. And so the application is, well, to combine signatures that have identically named types, type components. So say you have S1 and S2 that both define a type T and various operations over those types. And now you would like to write the combined signature S1 plus 2, that is a signature of modules that have type T and both sets of operations. So here is one way to write it. You say, without duplicating, without cutting and pasting all that, you just say sig type T, include S1 with T colon equals T. So what this does, it deletes this T, and then it substitutes T's here by the new T here, okay? And likewise, include S2 with T colon equal T, and in the end, so you will get a T component, all those val components, and all these val components, which is what you wanted at the beginning. And actually, if you're lazy, you can write that this way. You can just include S1 whole, that will bring a T in context, and then include S2 with T becomes T, which is going to remove that other T and use this T for those operations. And that's the kind of signature surgery that you cannot do with regular with type T equals tau constraints, because if you were to use those constraints here, multiple T components would remain. So here 3, one here, one here, one here, and here 2, 1, 2. And that's an ambiguous signature, and the type checker would reject that. All right, so I hope this is the end of the list of features. Yes. So well, let me conclude briefly, and then we'll have some time for questions and comments. All right. So well, I hope you will like OCaml 3.12. And so how can you help? I'm hearing that question in the audience. Thank you very much for asking it. Well, again, by testing, providing feedback as much as you can. That's really precious to us, because, well, testing is well, we do a little bit in-house with a few applications, a few key applications, but well, basically we still need help from the community. So if you want 3.12 to work, well, if you want your favorite CAML program to work with 3.12, the best thing to do is to test 3.12 with that program. So I'm still hoping to get some volunteers to work on parts of the system that we handle really badly. And again, I'm thinking about the Windows port and the Windows binary distributions. So I'm the only one in the whole CAML team who ever touches Windows. Okay, all others just recoil in horror. No, that's not right. Alain does a little bit of Windows as well, because, well, he has to, I guess. Yeah, because that's what the customers want. Lexifies customers. But anyway, so yeah, so Alain and I do a little bit of Windows, but still it's not a pleasure at all, and we are not experts. And so help would be most welcome. And for instance, you may have noticed that I did not release Windows binaries for 3.11.1 and 3.11.2. So I've been lazy, and it's a bit of an experiment. I'm waiting to see how many people are complaining, and hoping that someone will complain so loudly that I can tell, well, why don't you do it yourself? But so far that cunning plan hasn't worked well, so... So, yeah. Maybe it will work at some point. And then, well, there's also some community efforts that you may want to join. So one area where that I think is important for CAML is the packaging and distribution of CAML libraries and tools. And well, there are ongoing projects like, well, the Debian packages, Gaudi. Sylvain Legal is going to present a new proposal that looks quite exciting. But especially when it comes to packaging and distribution, that's really a community work. That's not the kind of work that one person can do alone. Okay, and so it would be good to have some community efforts around this. And well, by all means, keep up the good work that you're doing with CAML. Thank you. So we have plenty of time for questions, comments, discussions. Who's first? Yes.
If we want to use this, do we just check it out as CVS, or are there tarbles?
Okay, so it says VN now. So yeah, so in the Subversion trunk at this point, there's all the extensions except this one, which sits in a branch, and so Jacques Garrigue is going to merge it very quickly. So yeah, currently he's at some kind of meeting in a Japanese resort, but I'm not sure how much internet access he has in his ryokan. But as soon as he's back, that will be merged as well. Come on, don't be shy.
In the so why is the signature required in the module local module expressions?
That's a good question. Let's see, and maybe Alain will correct me. I guess so. When you build, when you inject the module into a first-class value, okay, so the module type inferred for that module can be of that form, but it can also be just a signature given in extension or something complicated, okay. So basically it's important that the user says explicitly, I want to see that module with this particular package type, because that package type then goes into the type of the first class value. And so for projection, I guess, yeah, so now you need to infer in the worst case, you don't know of any type for exp that can be alpha, okay, and then you need to infer a type and of that form, and well, basically the type checker again needs your help in saying this is the package type that I'm expecting, okay. In particular cases it could infer it, but in general it couldn't. So yeah, that's a little bit verbose. But again, that's a module language, right? It's a module where you say, that's a language where you say things. Well, just using names. I mean, these are basically names, possibly with some constraints. So these are not too big as far as annotations go. Yes. Microphone, please. Thank you.
Is there any subtyping in
at the core language level? No. I don't think so. So you mean between those types?
Yes.
I don't know, is there any? No, I don't think so, right?
That would be easy to implement, I guess.
I don't like those answers. Well, anyway, yeah. So yeah, maybe that could be merged, included within the the explicit subtyping that we have at the core language. Well, we'll see if there's a need. A question here?
So first of all, thanks for all these features. Most of them are really life-changing for a lot of us. A question about the bang operator in classes. So what is the semantics of inherit bang?
Ooh. I'm not sure because well, that was. So did you do that in your first extension, or was that added by Jacques?
That was added by Jacques. The meaning is that this specific inherit overrides some fields, some methods from a previous one. So if
some
you do
methods, so not all of them. Some.
So some of them, yes.
Okay.
Yes, I was wondering if there's any plans for support for integrating OCaml spotter or some other richer type annotations.
So yeah, that's one of the topics we discussed at the consortium meeting. But so yeah, we don't really have a plan of action yet. So I think everyone agrees that. Well, the compiler should generate abstract syntax tree annotated with types and locations and so on. So some kind of rich version of the abstract syntax. So currently we have a little bit of that in the annotation files, the one you obtain with -d types. But that's somewhat incomplete and kind of specialized towards just displaying the type of an expression when you click on it. So basically, we are definitely open towards extending these annotation files, those produced by -d types, and try to put kind of the union of the features that people need. But again, yeah, I guess that would have to be some kind of cooperative effort between OCaml Splatter and the other project that was done at Orsay before, and whose name escapes me, and so on. And yeah, so there are certainly a bit of engineering to define a common format and then implement it. So yeah, if you're interested, I just try to join forces with like the 2 or 3 existing proposals, and then I would be very happy to integrate this.
There is an incompatibility introduced by OCaml 3.12, which is when you have open format in your existing programs.
Yeah. Well, this one is gone, I believe. I was informed. Or at any rate, it will not be in 3.12.0. So yeah, that was an intentional extension of the format interface that was an extension of the format interface that caused an unintentional hiding with pervasive, and yeah, that broke surprisingly many programs. So we are backtracking on this, or maybe we have already backtracked on that. Someone told me about a recent commit that seems to be fixing the issue.
The issue is still open on the OCaml BTS.
Pardon me?
The issue is still open on the OCaml BTS.
Yeah. Well, it will be closed in due time. Don't worry. Hello?
Open bang.
Rejected. Okay, so well, thanks again. We are 5 minutes ahead of time. That's good for a timely lunch. And anyway, I will be here all day, so I'm looking forward to continue discussing. Thank you.